Hello and welcome to this video for the 2022 Level 3 Electricity paper for Level 3 Physics. So we're going to get straight into it. So question number 1, we're talking about AC circuits. So George is investigating AC circuits. He connects a 54 microfarad capacitor in series with a 36 ohm resistor and a 25 volt 50 hertz AC supply as shown in the diagram below. So we show that the reactance of the capacitor is 58.9 ohms. So reactance of the capacitor is the reactance is equal to 1 over 2 pi times F multiplied by the capacitance. So this is equal to 1 over 2 pi times of the frequency, which is 50, multiplied by the value of the capacitance, which is 54 times 10 to the power of -6. And this gives us an answer of 58.946 ohms, which rounds to 58.9 ohms in 3SF. And this is just a simple achieved level question, so just a plug and chug into the equation. Question B, we're going to calculate the circuit current. So to calculate the circuit current, we are going to need the overall impedance of the circuit. So we know that the voltage is equal to the current multiplied by the total impedance. And the total impedance, we need to consider the phasor diagram of the capacitor and the resistor. So in this case, if we draw a phasor diagram, we have our resistor R, and we know that the capacitance the reactance of the capacitor will lag the current by 90 degrees. So we have capacitance here. And the value we just calculated is 58.9 ohms. And the value of the resistor is 36.0 ohms. So if we do a vector addition here, we'll get the overall impedance. So we have vector addition here. So this will be 36.0, this will be 58.9, and this will be the impedance. And we can use Pythagoras theorem. So the impedance squared is equal to 36 squared plus 58.9 squared. So therefore Z is equal to square root of 36 squared plus 58.9 squared. And this should give us a value of 69.1 ohms, and that's the impedance of the circuit. And therefore, we can calculate the circuit current. So V equals to I times of Z. So therefore, we have the voltage, which is 25. That equals to 69.1 multiplied by I. Therefore, I is equal to 25 over 69.1. And that is equal to 0.362 amps. And that's our final answer for this question. So we have correct answer for the circuit current would be a merit grade. And you can get an achieved grade by calculating the correct impedance. So correct impedance would be up to here. Okay, cool. So we calculate the phase difference between the supply voltage and the circuit current for the circuit shown on page 2. We just state which one that leads. So we've already kind of did this one in the last part, but in this case, we're just going to calculate the angle. So we have our diagram here. So we have this, the resistor, and this would be XC, and this would be the impedance. So now trying to find this angle. So again, we can just use SOHCAHTOA. So in this case, we can use the tan rule. So tan of theta is equal to the opposite over the hypotenuse, which is equal to, opposite of the adjacent. And that is equal to XC over R. And that is equal to 58.9 over 36.0. So therefore, theta is equal to the inverse tan of 58.9 over 36.0. So therefore, the angle is equal to about 58.6 degrees. And we know that the current is in phase with the resistor voltage. So we know current is also in phase with the resistor voltage. So therefore, we're seeing that the supply voltage, which is in phase with our Z here, is actually lagging the current by 58.6 degrees. So therefore, the supply which we just calculated there is lagging. Supply is lagging the current or current by 58.6 degrees. Or you can say that the current is leading the supply. Leading the supply by 58.6 degrees. So either or should be fine here. So it does say to state which one that leads, so maybe just ignore this one here. So just focus on, so current is leading the supply by 58.6 degrees. So that's our final answer for this question, and correct value and correct statement is a merit. With either or of those should just be an achieved. So either or is an achieved. So explain how an addition of a suitable inductor to the resistor capacitor circuit with the AC supply can make the circuit resonate. So we should begin by explaining the meaning of resonance. So the resonance is when the circuit current is going to be a maximum. So this is going to occur exactly when the capacitance of the capacitor and the inductor is going to cancel each other out, because they're exactly out of phase of each other by exactly 180 degrees. So this will occur when XC is equal to XL. So therefore so this is when not the capacitance, but the reactance of the capacitor is equal to the reactance of the inductor, and therefore they cancel each other out. So therefore we get the maximum current in the circuit since impedance is at a minimum. So in this case, we just say that resonance will occur when XC equals to XL. So the impedance is at a minimum, and follows that the impedance of the circuit is just equal to the value of the overall resistance, so I equals to R, and therefore the current in the circuit is at a maximum. So the current in the circuit is a maximum, and it asks us how we can add an inductor. So so we can add an inductor to the circuit such as the reactance of the inductor equals to the reactance of the capacitor. And they will cancel each other out, so they cancel out. Since the of the capacitor leads the inductor by exactly 180 degrees. Okay, so we can add the reactance. We can add an inductor such as the reactance of the inductor is equal to the reactance of the capacitor, so XC equals to XL. And we can actually do a quick calculation here. So we have XL equals to 2 pi F times of L. And we know that the reactance of the capacitor was 58.9. So 58.9 equals to 2 pi F times of L. So L equals to 58.9 over 2 pi times 50. And we just get out the calculator. So 58.9 divided by 2 pi times 50. So L equals to 0.187 henries. So if we add an inductor of value 0.187 henries, we should be able to bring the circuit to resonance and have a maximum current. So this question should be an excellence level question if you can. So you're stating that resonance is when the current is a maximum, and this occurs when the impedance is at a minimum. And you can just say that the reactance of the capacitor is equal to the reactance of the inductor. So XC equals to XL, and Z equals, so the overall impedance is just the overall value of the resistance of the circuit. And we can say that when we add the inductor of the same reactance, we bring the circuit to resonance. So just those couple of points here. So X equals to XL, impedance is at a minimum, and current is a maximum, and we're adding an inductor such as this property holds. Okay. And the calculation is actually not needed, but I recommend it's really simple, easy, one-step calculation. So it shouldn't take much time. I recommend you do it. If you have enough information, then I do recommend that you just carry out the calculation to make your answer a bit more robust. But this here should be next. That's great. So looking at question 2 at electromagnetism. So David is investigating the inductors and magnets. He uses a 1.6 Henry 22.0 ohm inductor and connects it to a 12 volt supply. The inductor can be considered a pure inductor in series with resistor as shown in the diagram below. So in this case, when it says pure inductor here, it just means that this resistance here is 0 ohms. So we're not considering this inductor part to have any resistance. So the only resistance of the circuit we consider is only going to be coming from the resistor here. So therefore the resistance of the circuit equals to 22.0 ohms. So that's one thing we can keep in mind here. So overall resistance is 22 ohms. We want to calculate the circuit current after two time constants once the switch is closed and the current begins to flow. So in this case, we know that once the switch is closed, there's going to be a large rate of change of magnetic flux. So therefore, the inductor will try to oppose a change by inducing a voltage, which is going to act against that circuit voltage. So therefore, initially, the voltage is going to be 0 across the resistor, and it's going to be a full 12 over the inductor. As originally the pushing voltage of the inductor is just going to oppose that of the supply completely. So we know that initially, so just note down that initially the overall current equals 0 amps due to the due to the opposition, maybe perhaps due to the opposition from inductor. Okay, so in this case, so this is actually not really needed for the answer, but it's just good to check that you understand the concepts. So the first step here is we probably should try to calculate the maximum current, since we know that I at any time is equal to sum I max times of 1 minus minus the e to the power of t over t. Okay, so in this case, we know to use this particular equation, the 1 minus e to the power of t over the time constant. We know it's 1 minus because, like I said before, it's important to note that initially the current is equal to 0. So therefore, you can plug in when t equals to 0, e to the power of 0 equals to 1, so I equals to 0 amps. So it's good to keep these minds and concepts so you can reinforce your knowledge of which equation to use. So in this case, we're going to be using I max multiplied by 1 minus e to the power of t over the time constant. And we know that it's we're trying to calculate after two time constants. So it's I equals to sum maximum multiplied by 1 minus e to the power of 2. And -2, not 2. That's crazy. Okay. So the maximum current is going to be occurring when the voltage across the inductor is 0, and all the voltage is going to be across the resistor. Since the pushing voltage of the inductor is going to start dropping, and eventually when the steady state current is reached, the voltage across the inductor, so the pushing voltage of that inductor is going to be 0. So that's going to be when the maximum current occurs. So simply V equals to IR. And 12 equals to sum current times by 22, and I equals to 12 over 22, which equals to 0.545 amps. Sorry, running out a little bit of space here, but in this case we know that I equals to 0.545 multiplied by 1 minus e to the power of -2. And this will give us an answer of 0.471. And that's our final answer for this question. And this is a merit level question if you can get the answer. If you can get the correct value for the maximum current, it's going to be an achieved here. So maximum current here is achieved. Question B, we want to state the voltage across the pure inductor and the voltage across the resistor once the current is steady. So that's, as I just mentioned in the previous question, once the current is steady, the voltage across the inductor is going to be 0 since there's going to be no more opposition from the inductor, so that's going to be a 0. And the voltage across the resistor will just be equal to that of the source, so that'll be 12 volts. Yeah. And this will be an achieved if you can get both of them correct. Question C, once the current has reached a steady value, the switch is opened and the current falls to 0 in 2.5 times 10 to the power of -2 seconds. We want to calculate the size of the average induced voltage and state the direction of the voltage across the inductor. So the average size of the induced voltage is given by V equals to some value of the inductance multiplied by the rate of change of the current, or rather, if you don't like this notation, it's V equals to L times by the rate of change of current. So change of current over the time. To find the rate of the change in I, this will be the total, the final value of the current subtracted to the initial value of the current. So the total change is 0 minus 0.545, which is negative 0.545. But in this case, we can just worry about the absolute value. So in this case, we can just we can just take it as 545. And V equals to L times of 0.545 divided by the time, which is, what is the time? It's 2.5 times 10 to the power of -2. And the value of L is 1.6. So it'll be 1.6 multiplied by 0.545 divided by 2.5 times 10 to the power of -2. This will give us an average voltage of 34.9 volts. And the direction of this voltage will be the same direction as initially of the source, and that's because once the source is disconnected, there's going to be a large rate of change of flux through the inductor, and the inductor will try to oppose the change. So the change right now is that the current is decreasing, so therefore the inductor will try to oppose that change by pushing more voltage in the original direction of that source voltage. So we say induced voltage opposes the change, so opposes the change. And the change is a decrease in the current, so a decrease in current is change. And therefore, it's going to act in the same direction as the original source. So of original source. Okay. And that's it for this question, and this is a merit level question for the correct calculation and the correct direction. So merit level question. If you only get correct direction or the correct induced voltage, it's an achieved. So or, it's an or there, so either or of those would get you an achieved. 22 ohm resistor is replaced by a 44 ohm resistor and the switch is then closed. Explain by comparing qualitatively how much the changes will take place for the size of the maximum current drawn from the current circuit, the time constant, the energy stored in the inductor once the current is steady. Okay. So in terms of the maximum current, we know that the property of the maximum current is referring to that steady state current that we were talking before in question B. So that's when the induced voltage across the inductor is equal to 0 volts, and then the entire source voltage is going to be over that resistor. So that's going to be when the maximum current is drawn, so V equals to IR. And if the resistor is doubled, therefore the current will be halved. So therefore, if resistance doubles, if resistance doubles, then current maximum will halve since source is constant. So that will be part 1. So in terms of the time constant is equal to, so in this case it will be L over R. So in this case, when the resistor is doubled, therefore the time constant will be halved. So time constant will halve since resistance is doubled. Indicates that the maximum time, or the time it takes to reach the maximum current, will be reduced. So indicates the time it takes for the circuit to reach the steady state, or the maximum / steady state. And finally, in terms of the energy stored in the inductor, we know that energy equals to half Li squared. So therefore, we already mentioned that the current is going to be halved. So current at the maximum is halved. Therefore, the energy stored will be 1/4 of the and that's all we really need for this question. So we've covered all 3 points. We covered the current, the time constant, and the energy stored in the inductor. And if you can cover all of these points correctly here, that should be an excellent level grade. And for a merit, if you have any 2 statements of correct reasoning, then you'll have a merit. And for an achieved, you only need 1 statement that is correct. So current decreases, time constant decreases, or less energy stored in the inductor. So just the basic statements there will get you an achieved. Alright, so question 3, we're looking at capacitors and DC circuits. So Anne is carrying out some experiments using parallel metal plates to investigate the capacitors. She takes a pair of metal plates with an area of 0.16 meters squared and connects them to a 9-volt DC supply. The plates of the air-filled capacitor is 1 and is separated by a distance of 1 times 10 to the power of -3. We want to show that the capacitance of the capacitor is 1.42 times 10 to the power of -9 farads. Okay. So this is just another plug and chug question. So we have the capacitance is equal to the relative permittivity multiplied by the dielectric constant, which is 1. So E air is 1 multiplied by the area divided by the distance between the plates. So this C is equal to 8.85 times 10 to the power of -12 multiplied by the dielectric constant, which is in this case we're using 1, multiplied by the area, which is 0.160, all divided by the distance, which is 1 times 10 to the power of -3. And this should give us an answer of 1.42 times 10 to the power of -9 farads. And this should just be an achieved level question for the correct answer, just plug and chug. Question B, calculate the energy stored in the capacitor once it's fully charged. So the energy stored in the capacitor is given by E equals to half CV squared. Once the capacitor is fully charged, the pushing voltage of that capacitor is going to be equal to the initial source voltage. So overall, at that point, it's some sort of equilibrium that's achieved. So since it's in the opposite direction of the source, the pushing voltage, and it's the same size, no more charges can flow. So therefore, there's no charges flowing in the circuit. Current is equal to 0. And at that state, there's an equilibrium and the maximum voltage is reached. So therefore, we're just saying that max voltage, when V of the capacitor is equal to the source. So therefore, E is equal to 1/2 of the capacitance, which we just calculated as 1.42 times 10 to the power of -9 times by the 9 squared. And that's going to be equal to 5.75 times 10 to the power of negative 8 joules. Part II, we want to describe the effect of the energy stored on the capacitor when a sheet of mica with relative permittivity of 7 is introduced between the capacitor plates. So in this case, when we add the sheet of mica, it's going to polarize the charges. So in this case, there's going to be some attraction between the charges on the capacitor and that in the sheet of mica. So therefore, this will increase the overall capacitance of the capacitor. So therefore, more charge can be stored before a certain pushing voltage is reached. So in this case, if we just want to refer to the formula, so C equals to A over D. So C is proportional to the permittivity. So in this case, if the permittivity the permittivity is increased, the capacitance increases by 7 times. Energy is proportional to the capacitance, so therefore at the max voltage, the energy will increase by 7 times. So that's really all you need for this question. So you can go into a bit more detail if you really want to, but it's not really needed at this level. So at this level, you really just like look at the formula. And if you want to look at the formula, you're just saying that, oh, okay, so permittivity increased by 7 times, capacitance is proportional, so therefore capacitance increased by 7 times, and energy proportional to the capacitance, so therefore energy increased by 7 times. That's really all you really need at this level. But if you want to learn more, you can talk about like how the charges on the plates have some sort of attraction to that of the mica, reducing the repulsion. So therefore, there's going to be a lower pushing voltage at a certain number of charge. More charges can be stored, so therefore more energy will be stored once the maximum voltage is reached. So in terms of NCA, really all you need is just this here. So that's a merit level question for both the correct answer and explanation. Achieved level grade will come with either or. So either or. Cool. Let's look at question C. So Anne then disconnects the plates from the 9 volts DC supply so that the plates are electrically isolated. She then pulls the plates apart. So explain what happened to the charge on the plates and the voltage across the plates. Alright, so in this case, she disconnected the plate, so therefore the charges can't really flow anywhere, so therefore the charges on the plates is actually going to stay the same. Okay, so charge cannot flow, so charge stays the same. And in terms of increasing the distance, assuming the area stays the same, we know that C is proportional to 1 over D. So increasing distance will decrease the capacitance, so capacitance will decrease. Very messy writing, apologize. Let me try again. So capacitance will decrease. So capacitance is decreasing, and we know that charge is equal to the capacitance times the voltage. So therefore, in this case, the charge is staying the same, but we're decreasing the capacitance, so therefore, the voltage induced will be increased. And in this case, so we can note that E equals to half CV squared. So in this case, just as a side note, not really relevant to this question, you can just skip on the video if you don't want to watch. So E equals to half of C times V squared. So the voltage induced across the plates will be increased, but the capacitance will decrease. But in this case, we know that E is proportional to voltage squared, but only proportional to C. So but the voltage increases at the same factor that the capacitance decreases, since charge is the same. So therefore, the energy is actually going to increase. And where does this energy come from? The energy actually comes from the work that Anne is doing from moving the plates apart, which is actually where the energy is coming from. So energy increases comes from work done by Anne to separate the plates, which is actually very interesting. So I just thought I'd leave that as a little bit of a side note, but in terms of the question, just don't worry about that. So that's where the question is. So that will get you a merit grade. And if you have one correct statement, so for example, capacitance decreases or the plate's distance increases, so any one correct statement will get you an achieved there. Okay. Anne is then experimenting with connecting different capacitors in series and in parallel across the 12-volt supply, and it's shown in the diagram below. Calculate the voltage across the 4.7 times 10 to the power of 2 microfarad capacitor. Begin your answer by calculating the total capacitance. Okay, so that's a question. So the total capacitance. So let's try combining these two capacitors into a single capacitor in series. So the capacitor will be, in this case, it would be the sum. So in this case, CT equals to C1 plus C2, which is capacitors. So the capacitors in parallel will be equal to C1 plus C2. So we'll just do microfarad. Okay, make this a little bit easier to read. We'll just do 600 microfarads plus 200 microfarads. That equals to 800 microfarads. And the total capacitance of the circuit is equal to 1 over CT equals 2. Probably shouldn't use CT before. We'll just use CP for parallel. So CP. That equals to 1 over 4.7 times 10 to the power of 2 microfarads plus 1 over 800. So therefore the total capacitance is equal to 296 microfarads. So that's the total capacitance. That's the total capacitance of the circuit. So basically this circuit, you can just rewrite this one as so this is the same thing. So 296. It's equivalent to one capacitor of 296 microfarads. And we probably want to calculate the total number of charge across this, just like convert it into one capacitor, so the total charge. So we know that Q equals to CV. And we want to find, so at the maximum, so 12. So at the maximum, it's equal, the pushing voltage is equal to 12, the maximum equal to the supply. Therefore, Q equals to 296 times 10 to the power of negative 6 times of 12. That equals to 3.552 times 10 to the power of negative 3. Coulombs. I'm so sorry about that. My mind just blanked. So 3.552 times 10 to the power of negative 3 coulombs. And to find the voltage across the, in this case, the 4.7 times 10 to the power of 2 microfarads capacitor, we can use the same equation. So Q equals to CV. So V equals to Q over C. So in this case, V is what we're trying to find. So V equals to 3.5 divided by the capacitance. And that is equal to 7.56 volts. Yeah, we can do this one. We can just say that it's equal because in this case, we have the 4.7 times 10 to the power of 2 microfarad capacitor. Is considered in series, and in this case, the same number of charge will be stored, so we know that the charge is the same in this case. So 7.56 is the final answer for this question, and to get a merit, you need total charge is merit, and total capacitance is an achieved. Oh, sorry, wrong place. So this isn't achieved here. And this here is the merit. And I think that's it. Yeah, that's it for this paper. And I hope you enjoyed, and I hope to see you all in the next one.